Let's do some real math. Okay, sorry, let me fix my board here. All right, so let's do one or two more implicit problems, and then we'll kind of move along. Okay, stop converting, finally. So let's say I want to find the derivative dy dx for the equation, let's make it real fun and exciting, sine of x squared y plus 2x cubed y to the fourth equal to, let's not make this, sounds like it's going to be gross already, James, x to the fifth plus y. So again, I really just want to remind everyone of how implicit works, right? We are making the assumption, it is implied, that's why it's called implicit, that y is a function of x, or at least depends on x in a functional sort of way. So that when we differentiate, right, when I see y, I really think, oh, y, you're some function of x. Or some stuff. And I want to make this y squared. It's a little more exciting. So when I take the derivative of sine of x squared y, well, I'm going to have to repeatedly use the chain rule here and the product rule. Okay. So what's the derivative of sine of x? Derivative sine of x is cosine of x. So the derivative sine of some stuff is cosine of the stuff times the derivative of the stuff. I'm going to do this one kind of the long way, even though I normally wouldn't. So it's cosine of my stuff times the derivative of that stuff, which we'll do in the next step. The derivative of 2x cubed y to the fourth, we're going to have to use the product rule. And I really, really encourage you, when you have a constant in your product rule, don't think of this as a triple product. That seems crazy. And you could say, well, it's 2 times x cubed y to the fourth, and then just do the derivative of that and then distribute the two. But I think it's easiest to think of it as 2x cubed, one piece of the product, times y to the fourth, other piece of the product. So using the product rule, the derivative of 2x cubed is 6x squared, times, leave the other thing alone, plus, leave the 2x cubed alone, times the derivative of y to the fourth is, well, the derivative of some function to the fourth power is 4 times my function to the third power times the derivative of my function. So it's going to be 4 times y cubed times, I'm going to write y prime instead of dy dx because it's easier to write y prime, equal to the derivative of x to the fifth is 5x to the fourth. The derivative of y squared, or some stuff squared, is 2 times my stuff times the derivative of my stuff. So that's our first step, take the derivative. I guess we should also finish it. So let's see. So the problem is these problems always get messy, right? It's just like a lot of writing. Let's see, I've got cosine of x squared y times, okay, derivative of x squared y, I'm going to have to use the product rule again. So it's going to be 2x times y plus x squared times, you can either say the derivative of y is 1 times the derivative inside, which is y prime, or you can just say the derivative of y is the derivative of y, which is y prime. Right? I know, like, oh yeah, it's just, I'm saying the thing when I say, what's the derivative of y? Oh, I just told you, it's the derivative of y. And then plus all this garbage, which I guess we can simplify a little bit. This is 6x squared y to the fourth. This is 2 times 4 is 8. X cubed y prime equal to 5x to the fourth plus 2y prime. This problem has an additional wrinkle in that this part is problematic. Right? I want to solve for y prime, which means grouping all my y prime terms on one side and all my not y prime terms on the other side. But the problem is this kind of, if I try and group all of this on the same side as the y primes, and then factor out a y prime, I can't really factor out a y prime from here. What I have to do first is distribute. I have to distribute this cosine of x squared y to each of these things here. So yeah, this is a lot of writing. Okay, so what do I get? I get, and I'm going to write it in the more standard way, which instead of writing cosine of x squared y times 2xy, I'm going to write it as 2xy times cosine of x squared y. So I get 2xy times cosine of x squared y plus x squared y prime times cosine of x squared y. plus all the rest of the stuff. 6x squared y to the fourth. Jesus, why did I come up with such a long problem? Sorry. Oof, okay, and then we can actually group our y prime terms together. So I've got a term with a y prime here, and a y prime here, and a y prime there. So it doesn't really matter which side you decide to bring everything to. I'm going to bring all my y primes to the left, all my non-y primes to the right. I am going to do two things at once here because I'm running out of room. So I'm going to bring my y primes to the left. I'm also going to factor out the y prime. So if I factor or divide out the y prime from each of these, I'm going to get x squared times cosine of x squared y plus 8x cubed y cubed. Right, I'm removing the y prime minus, right, because it's coming over to the left, 2y. And it's all of that times y prime. And then it's equal to the non-y prime thing. So this minus this minus this. So 5x to the fourth minus 6x squared y to the fourth minus 2xy cosine of x squared y. Finally, of course, I think I can fit it in at the bottom, but it's going to be a little bit close. To get y prime, we divide both sides by this giant factor here. So y prime is going to be all of that divided by all of it. So it's going to be 5x to the fourth minus 6x squared y to the fourth minus 2xy cosine of x squared y divided by all of this. X squared cosine of x squared y plus 8x cubed y cubed minus 2y. And that would be your derivative, which is terrible, but fine. And no one in their right mind would ever ask you to find the second derivative of this, because finding the second derivative would require an insane quotient rule. And then for every y prime that showed up, you'd have to plug in this thing you just found, which is rule. Yeah. I meant to find Yeah, go ahead.
How did you find, I'm still confused on how you found, how you times y prime after the 4y cubed and the 2y.
Sure. Let me ask you a different question. This question is for everybody. What's the derivative of x cubed plus 2 to the fourth power? Well, I've got some stuff to the fourth power, right? The derivative is 4 times my stuff to the third power. And then what do I have to multiply by?
The derivative of the inside. Jeez.
Exactly. That's exactly what's happening here. I'm taking the derivative of some stuff to the fourth, and I'm getting the derivative is 4 times my stuff to the third times the derivative of the inside. That's what y prime is. It's the derivative of the inside.
You don't have to define it. You just you don't have to find the exact.
So here's the thing. And here's I'm going to go back to the name. The name is implicit differentiation because it is implied, but not explicit, that y is a function of x. So if you've got some derivative of some function of x to the fourth power, the derivative is 4 times that function to the third power times the derivative of that function. Does that make things more clear, or would you like me to talk more? I'm happy to talk more about it.
Maybe one more example will help.
Sure, yeah, no problem at all. So, yeah. So let's look at one more example, and let me grab a new green pen. Yeah. So let's say I wanted to, yeah, sure, got pens in all my pockets. I want to find y prime for the following. I'm going to make this one less terrible. Yeah, for x cubed y to the fifth plus 6xy equal to 18 minus y to the 7th. Okay, so I'm going to differentiate here. So first step, differentiate both sides. Here I'm going to use the product rule. But again, I'm thinking of y as some function of x. I don't know what it is. I could try my heart out to solve this for y and get y as a function of it. It's not going to happen. But here's the point. I don't need to know what it is. I'm gonna rewrite it in a way. So let's pretend that y was equal to, I don't know, something simple like x squared plus 1. So I could pretend, I'm going to do that later. I'm going to do it first. So let's say instead, so I'll come back to here for a second. So let's rewrite this as x cubed times x squared plus 1 to the 5th plus 6x times x squared plus 1 equal to 18 minus x squared plus 1 to the 7th. And if I start differentiating this, let's start with the right-hand side just because it's going to be a little easier. The derivative of some stuff to the 7th power is 7 times my stuff to the 6th power times what, everybody?
$2x.
The derivative of my stuff. Exactly. 2x. And then it would be negative, right? Because there's a negative sign out here. And then the derivative of 18 would be 0. But so let me just point out, right? When we start differentiating this, again, I'm thinking that y is a function of x. So when I differentiate this right-hand side, I'm going to get 0, derivative of 18 is 0, minus, all right, what's the derivative of some stuff to the 7th power? It's 7 times my stuff to the 6th times
the derivative of the inside, y prime.
Exactly, the derivative of the stuff, y prime. These are exactly matching up, right? Where this is like my y to the 6th, and this is like my y prime. So that's the idea. We don't actually know what y is, but we know it's like a function of x. And so when we differentiate some power of y, we have to treat it like a chain rule and say, oh, I've got some stuff to a power. Some stuff to a power. The derivative is that power times that stuff to the 1 less power times the derivative of the stuff. Chain rule. And that's why you'll hear me say a lot that implicit differentiation is really just the chain rule. We're just using the chain rule where we're thinking of y as a function of x. The reason we don't apply the chain rule part to the x parts is because you could, but if you multiply by the derivative of the inside, the derivative of x is just 1 because we are differentiating with respect to the variable x. Okay, so I guess we should finish this problem, even though I don't really want to. The derivative of x cubed y to the 5th is going to be 3x squared times y to the 5th, right? That's the first half of the product rule, plus x cubed times, okay, the derivative of some stuff to the 5th power is 5 times my stuff to the 4th times the derivative of that stuff. And then for 6xy, I personally would like to think of it as 6x times y. So when I use the product rule, the derivative of 6x is 6, leave the y alone, plus 6x we leave alone, and the derivative of y is the derivative of y. After we differentiate both sides, the rest is doing the algebra, which isn't hard in that we don't have to think of new things, right? It's not like it's there's a word I'm looking for, I'm not finding. It's not like it's some new challenging process. It's just that sometimes algebra is also challenging because we have to be careful about keeping track of all the little pieces. So I want all the y primes on the same side. I want all the not y primes on the same side as well. So since all the not y primes, namely this and this, are already on the left, I should leave them on the left and bring all the y prime things to the right. So I'm going to have 3x squared, y to the fifth, plus I'm going to rewrite, I'm going to have this, sorry, plus 6y equal to negative 7 y to the sixth times y prime minus 5x cubed y to the fourth y prime. We do like to write the coefficients first. Minus 6x y prime. I'm going to cheat a little bit because I'm tired of writing all of this. I'm going to factor out a y prime. So I'm going to divide out a y prime and write it at the end. I know it's kind of, I always hated when my teachers did that, but I can understand why they did it because writing all this stuff is just like, oh my God, so much stuff to write. So I factored out the y prime, and then I'm going to divide by this on both sides. So I'm going to get that y prime is equal to 3x squared y to the fifth plus 6y divided by all of that. Negative 7 y to the sixth minus 5x cubed y to the fourth minus 6x. And it will almost always be the case that you cannot simplify this, right? There's nothing you can factor out. Well, I should say you could factor out a y from the top, but there's no common factor that you can factor out from the top and the bottom that you can cancel out. The exception sometimes is a constant that you can factor out from the top and the bottom that you can cancel, but I really, really wouldn't worry about that. Typically, once you get here, you're like, I am sick of this problem. Let's just be done with it. So that's the main thrust of implicit differentiation. We can solve equations like this where y is implicitly thought of as a function of x, but cannot be found explicitly. We can still find the derivative in terms of x and y. I should point out that sometimes, I don't know, this is not a good example. I can make it one, no. Sometimes people will ask you to find the equation of a tangent line. So let me give you one more example. Just because we should say one more example. I'm going to try and make it not super ridiculously hard. Good luck, James. Oh yeah, I should do, I'm smart. I can be smart sometimes. So let me think a little bit harder about a question. So I want to find the equation of the line tangent to the following. Let's see. Sine of, what do I want to make what? Sure, sine of x squared plus y. Yeah, that would be fine. Oh, I have to be smart though. Sorry, the problem is it's not really a problem. Let me think for one moment here. That's always boring. Let's just make it sine of x squared times y. Sure. Plus x to the fourth equal to, sure, 1 plus y cubed. So find the equation of the line tangent to this at the point 1, 0. Sure, that seems all right. And there's two there's two routes you can take. They both start at the same place, which is finding the derivative of both sides. So whenever you're trying to find a slope of a tangent line, right, which we have to find the slope, we're trying to find the equation of the tangent line, you take the derivative. And when it's this, where you've got x's and y's all kind of mixed together, you can't solve for y, you have to do it implicitly. So first step, we differentiate both sides. So derivative sine of x squared y is cosine of my stuff times the derivative of that stuff, which is going to be product rule. There's usually a lot of product rule in these implicit problems. Derivative of x squared is 2x times y plus x squared times y prime. Plus the derivative of x to the fourth is 4x cubed equal to derivative of 1 is 0. The derivative of y cubed, or some stuff cubed, is 3y squared y prime. I know we did one like this last time, but I do want to emphasize this comes up a lot. You can, at this point, if you want to, I don't want to, but you can solve for y prime in terms of x and y. You totally do that, and then you can plug in x equals 1, y equals 0, and get the equation or the slope of the tangent line. But you could also just plug in x equals 1 and y equals 0 now. And I know I said this last time, but I want to say it again because it is something that makes it easier. So if you're ever asked to just find the equation of the tangent line or just find the slope of the tangent line, and you're not actually specifically asked to find the derivative in terms of x and y, you might as well go ahead and plug in 1 for x and 0 for y, especially because plugging in 0 for y is going to make a lot of things go away. So I plug in 1 for x and 0 for y, I get cosine of, 1 times 0 is 0, so cosine of 0, which is 1, times 2 times 1 times 0, hey, that's 0, plus 1 squared times y prime, that's y prime. Well, this just got a lot easier. That's just y prime. Plus 4 times 1 cubed is 4, equal to 0 plus 3 times 0 is 0 y prime. Okay, look what I got. I got 1 times y prime plus 4 equals 0, so y prime equals negative 4. So the slope of the tangent line at this point 1, 0 is negative 4. And then we can find the equation by saying, okay, well, y minus the y coordinate equals negative 4 times x minus the x coordinate. And then if you want to write it in the, especially if you got y minus 0, you should at least write this left side as y. You can leave it as y equals negative 4x minus 1, or you can write it as negative 4x plus 4. But I really, really want to recommend that if you're doing implicit and you're only trying to find the slope of the tangent line or the equation of the tangent line and not the derivative as an expression in terms of x and y, you don't need to do all the terrible algebra. You can just plug in your point right after you differentiate both sides. It usually makes things a lot easier to solve for. All right, let us move on. We're going to move on, but we're not going to move on, meaning we're going to do other things, but we're still going to use implicit because although I know I have said a lot that typically when we are finding the derivative of a new function, we often go back to the limit definition. That's not always true. A lot of the times we go back to the limit definition, but sometimes, like for the trig functions, tangent, cotangent, secant, and cosecant, we use the quotient rule and other things we already know. And for some other functions, like the natural log of x and the arcsine and the arctangent and the arcsecant and the other ones, we find the derivative of those inverse functions by using implicit differentiation. And we're going to start with kind of the one that you might already know. I want to find the derivative of the natural log of x. And I will say you can do this one using the limit definition. There's definitely a way of doing this, but I'm not going to. So if you want to find the derivative of a function and you think you might be using implicit, well, I shouldn't really say that. The idea here is that we're going to rewrite some things. If you know a function is invertible, so it has to be a function that has an inverse function, then you can kind of do what we're about to do. So I'm going to say, well, it's really going to be easier if I rewrite this. I'm going to say, well, I want to find the derivative, which is not what I actually write. So I want this, but I'm going to think of it as I'm finding the derivative of the function y equal to the natural log of x. And I want to write it as an equation so I can actually solve for x as a function of y. So I'm going to rewrite this as e to the y equal to e to the natural log of x, which is x equal to e to the y. And now we're going to differentiate that implicitly. So I'm going to say, okay, I've got x equal to e to the y. I'm going to take the derivative of both sides with the knowledge that y is a function of x. I know y is a function of x. I literally wrote it that way. Y is a function of x for sure. It's not even implicit, it's explicit. But we're still going to use implicit because we can. So we're going to differentiate both sides. Okay, this is an easy one. What's the derivative of x?
1.
1. This is a slightly harder one. What's the derivative of e to the y?
E to the y. dy.
That's most of it.
Or y prime.
Right.
Yeah.
So again, just like before, when you're taking, I should have done e to the y before. When you take the derivative of, y to the third, or some stuff to the third. It's 3 times my stuff squared times the derivative of my stuff. Well, when you take the derivative of e to the stuff, it is e to the stuff times the derivative of the stuff. Just like the derivative of e to the x squared is e to the x squared times 2x. It's the exact same idea of the chain rule. Okay, but now we're going to solve for y prime. So check this out. Divide both sides by e to the y. So y prime is equal to 1 over e to the y. And then whenever you're doing this process where you're trying to find the derivative of some function of x, we should know what this bottom part's equal to, or whatever you have left over. Right? This y is equal to the natural log of x, or you could even just say, I know that e to the y is equal to x. So you could replace and say, I've got 1 over e to the natural log of x, but you can just make your life easier and say, oh, look, I know that e to the y is equal to x. So 1 over e to the y is equal to 1 over x. And that's it. We have done it. We have found the derivative of natural log of x. The derivative of the natural log of x is equal to 1 over x. Definitely one you want to memorize. Okay. And now, since we're in a chain rule kind of mood anyway, we might as well talk about the chain rule version of this. So if I was to take the derivative instead of, say, the natural log of, now let's make it interesting, like sine of x. Okay, I'm just going to apply the same, really it's kind of like, I'm just using the same words every time. When I take the derivative of the natural log of x, I get 1 over x. I'm going to replace the x's with stuff. Your natural log of some stuff is going to be 1 over the stuff. And since I said the magic word stuff, I have to multiply by we have to multiply by the derivative of the stuff. So the derivative of the natural log of x is 1 over x. I'm going to write this shortly. The derivative, in fact, why even wait? The derivative of the natural log of some stuff is 1 over the stuff times the derivative of the stuff. I like to think of it that way because it's more clear to me that the chain rule is really in action. Right? I did my derivative of my outer function. Oh yeah, the derivative of natural log is 1 over the stuff. And then after that, I multiply by the derivative of the inside function. But some people, and I totally understand why you would want to write it this way, some people prefer to write this as the derivative of the stuff over the stuff, which is also a perfectly legit way of writing it. But I like to, at least I say it this way in my head, even though I might write it this way. So in this case, it becomes 1 over sine of x times cosine of x, which you could leave that way, but you should probably simplify as cosine x over sine x, which is cotangent of x. So that is the chain rule version of the natural logarithm. Just like every function, there's a regular derivative, like the derivative of tangent of x is secant squared of x. And then there's the chain rule version. The derivative of tangent of stuff is secant squared of stuff times the derivative of the stuff, right? It's always just replace the x's with stuff and throw on a derivative of the stuff at the end. Let's do a couple more examples. Natural log. How about the derivative of the natural log of, I don't know, something crazy like x to the 4th plus 1. Sure. Pretty straightforward. The derivative is going to be 1 over x to the 4th plus 1 times the derivative of that, which is 4x cubed. Which you could leave like this, or you might rewrite it as 4x cubed over x to the 4th plus 1. And that's as simple as it gets, right? There's no simplifying we can do to that. On the other hand, I do want to point out a slightly different problem. What if I take the derivative of the natural log of, I don't know, x to the 6th? Sorry, 1 second. I think there's a smoke alarm going off in my house. Not that I think there's no fire. I just want to check. No, I think it's my neighbors actually. I think there's some close off. I guess I should look at their house to make sure it's not on fire. No, nothing seems to be on fire. I think everything's okay. All right. Anyway, back to our regular scheduled program. So the derivative of this is going to be 1 over our stuff times the derivative of our stuff, which is 6x to the 5th, which we could totally write as 6x to the 5th over x to the 6th. And then we actually could simplify this further. We could cancel out an x to the 5th and 5 of the x's there and get 6 over x. And the reason I mentioned this specifically is because there's something else we could have done in the beginning if we'd wanted to, which is I could have used one of my logarithmic rules that says, oh, if you have the natural log of something to a power, that power can come down in front. And I could have rewritten this as the derivative of 6 times the natural log of x. And then if you've got a constant times a function, the constant hangs out. And the derivative of the natural log of x is 1 over x. And look, that's exactly what that is over there. It's 6 over x. So a lot of times we like to use these rules of logarithms to make our differentiation life a little bit easier. Let me remind you of the rules in case you have forgotten them. Oh, let me not trip on my chair. So the rules we typically like to, what's the word I'm looking for? I don't know. Use, manipulate, exploit. That's the word I really wanted. If you have a log, doesn't matter what the base is, any base. The log of a product is equal to the log of the first thing plus the log of the second thing. So log base b of a times b equals log base b of a plus log base b of b. And if you have division, log base b of a over b equals log base b of a minus log base b of b. And finally, the one we just used, log base b of, how did I write it over there? Of a to a power p is equal to p times log base b of a. And the result here is that essentially, so, right, I could, let me write this. So I could ask you a question like, find the derivative of the natural log of x cubed times sine of x. And you could do it the hard way. You could say, well, I'm going to say, all right, the derivative is 1 over the stuff times the derivative of that stuff. And then I'm going to have to use the product over the derivative of the stuff. So I'm going to get, I don't know what, the derivative of x cubed sine x is 3x squared times sine of x plus x cubed times cosine of x, all over x cubed sine of x. That is certainly a fair and legitimate way to do it, but I would rather make my life easier. I would rather say, well, this I could rewrite. This is equal to the derivative of the natural log of x cubed plus the natural log of sine of x, which is equal to, I'm going to go even further and simplify this as, I'm still writing the derivative because I haven't differentiated yet. I'm just using my log rules. Derivative of 3 natural log of x plus the natural log of sine of x. And then differentiating that is super straightforward. I don't have to use, I guess I have to use the chain rule here, but like, it's a lot less. It's going to be 3 times 1 over x plus derivative of natural log of sine we did before. It's 1 over sine times the derivative of sine, which is cosine. It's also a lot simpler looking, right? This is 3 over x plus cotangent of x. That's a lot nicer looking than this huge mess over here. They are the same. You just have to do work with this one to simplify it to get it to look like that. So usually a good rule of thumb is if you're taking the derivative of the log of some complicated garbage, you typically want to use these rules of logarithms to make it less complicated. And if I will say this example isn't too bad, right? This one is pretty manageable without simplifying it. Let me give you one that is worse. And if it were me in regular times, I would definitely write a test question like the following. And almost without a doubt, someone would do it the hard way, which is too bad because it takes a lot more time to do it the hard way. So I want to find the derivative of y equal to the natural log of some gross thing like x to the 7th times secant of x divided by, this pen is dying already, loser pen, e to the 4x plus 1 times the square root of x cubed plus 8. Well, that looks awful. I'm definitely going to simplify this before right? So you really could do it the long way and say, okay, the derivative is going to be 1 over all of that stuff, and then times the derivative of all that stuff, which you'd have to use the quotient rule, and then the product rule for the top and the bottom, and then also the chain rule for a couple of these things. Don't do it that way. Rewrite. So I'm going to rewrite this as, and again, I'm not taking the derivative yet, so I'm not going to write that I'm taking the derivative yet. Also, let me do one thing real quick here. Oops. Sorry, I was gonna take a picture, but then someone came back in. Let me just capture all you guys. I've caught you all, like Pokemon. All right, so I'm rewriting this. So I like to do it all in like 2 steps, but you could do it in more. The thing I want to say is I see that I have 4 factors. I have x to the 7th times secant of x divided by e to the stuff, and also divided by the square root of x cubed plus 8. Those are 4 things that are multiplied or divided together. You could do it the long way, meaning not the long way, but like you could simplify it the long way as it's the natural log of the top part minus the natural log of the bottom part. And I definitely want to rewrite the square root of x cubed plus 8 as x cubed plus 8 to the 1/2. And then I'm going to break these up again using the rule for the logarithm of a product. This is going to be the natural log of x to the 7th plus the natural log of secant of x minus the natural log of e to the 4x plus 1. Yeah, I'm going to go ahead. I'm going to make a mistake. Plus the natural log of x cubed plus 8 to the 1/2. And what's my mistake? My mistake is that it's really minus all of this. And all of this natural log of e to the 4x plus 1 times x cubed plus 8 to the 1/2. This is equal to the natural log of e to the 4x plus 1 plus the natural log of x cubed plus 8 to the 1/2. But it should be minus all of that. So let's bring down the powers, then I'm going to say something. So bring down the 7. So I get 7 natural log of x. There's no power to bring down here, so I'm just going to write it as the natural log of secant of x. You could also write it as the natural log of 1 over cosine, but I don't think you want to. Minus, so the natural log of e to the 4x plus 1 is just 4x plus 1. Right? The power comes down, and then the natural log of e is just 1. Minus 1/2 the natural log of x cubed plus 8. Couple things. Thing 1, the thing I always think about being true. You can simplify this by saying all the factors in the top end up with positive coefficients, and all the factors in the bottom end up with negative coefficients. That's what I always think about. So I would probably skip this step and go straight to this step where I actually have it as this. I would probably go straight from here to here, be like, oh yeah, it's the natural log of the top factor plus the natural log of the top factor minus the natural log of the bottom factor minus the natural log of the other bottom factor. I think that is a perfectly legit first step. And then the second step is bringing down the powers. The other thing I want to point out, which I imagine some of you are like, I see another power I can do something with. You cannot bring this 3 out because the 3 is not the power on the whole thing. And I feel like some of you are like, well, James, couldn't you say x cubed plus 2 cubed and then say that's x plus 2 cubed? And I know I like to think none of you actually want to say this because you know this is not true. X plus 2 cubed is not x cubed plus 2 cubed. X plus 2 cubed is x cubed plus other things. It's x cubed plus what? Oh, now I feel like I have to. It's x cubed plus 6x squared plus 12x plus 8. Right? There's a lot of middle terms here that x plus 2 cubed, that x cubed plus 2 cubed is not. So this, you cannot bring down the powers anymore. It has to be the power on the entire expression, and we don't have that here. And now, finally, I've gotten this as simply as possible. I'm going to take the derivative. So my derivative is going to be 7 times 1 over x plus 1 over secant of x times the derivative of secant, which is secant x tangent x, minus the derivative of 4x plus 1 is just 4, minus 1/2 times the derivative of the natural log of x cubed plus 8 is 1 over the stuff times the derivative of the stuff. And if no one was asking me to simplify, I would probably leave it like this. I might convince myself that I should at least cancel the secants though. So my answer here, if you want to simplify it a tiny bit, is 7 over x plus tangent of x minus 4 minus, I would probably write this last part as minus 3/2, right? 3 times 1/2, and then x squared over x cubed plus 8. I would probably write it that way. So the idea here really is that if you've got a logarithm, whether it's a natural log or a different base, which I'm going to talk about next, you want to, of some garbage, right, of some terrible stuff that you can break apart into smaller, simpler logs, you want to do that. And your professor wants you to do that because it's going to be easier to differentiate. Okay. I think, let's see, what else do I have to say here? Yeah, I should say that. Okay, cool. So what if we have a different base? What if I wanted to instead say take the derivative of log base 3 of x? Well, could we do that? No, I guess we don't really have the tools to do that yet. That's kind of the next thing. So here's the way we can do this. There's a couple ways you can do this. The easiest way is to use the change of base formula. So change of base formula says log base 3 of x, or log base a of b, is equal to whatever base you want. I'm going to pick base e. So it's log base e, or natural log of x over the natural log of 3. I can definitely talk about this. In fact, I'm going to talk about it. You guys don't have a choice. So why does the change of base formula work this way? Well, because of the following. If I say y equals log base 3 of x, I really don't want to write it that way because, well, one, it's just not nice. Two, if I'm trying to use a calculator to approximate things, most calculators don't have a log base 3 button. They have a log base 10 log button and a natural log base e button. That's kind of it. But I can rewrite this. I can use the fact that this is really just an exponential equation, 3 to the y equals x. And then I can take the log using any base I want on both sides. You could use log base e, log base 10, log base something else that's convenient. I'm going to use log base e, which is natural log. So the natural log of 3 to the y equals the natural log of x. Bring the y down in front. So y times natural log of 3 equals natural log of x, and then y equals the natural log of x divided by the natural log of 3. So y, which is log base 3 of x, is equal to y, which is natural log of x over natural log of 3. And I do think it's kind of nice that when you write a logarithm, the base is like in the subscript, it's lower, so that you can say, oh yeah, if I'm doing log base 3 of x, well, the thing that looks lower ends up in the denominator, and the thing that looks higher ends up in the numerator. That's kind of, I think, convenient. And then here's what you have to remember, and this is something that people, I feel like, sometimes have a hard time convincing themselves. Natural log of 3 is a constant. There are no x's there. And so I'm going to treat it like a constant. All right, what's the derivative of x cubed over 4? It's 3x squared over 4. And when you divide by a constant and you take the derivative, the constant just hangs out, whether it's in the numerator or the denominator. If you multiply by a constant, it just sticks around. If you divide by a constant, it just sticks around. So the derivative of the natural log of x over the constant is, well, the derivative of natural log of x is 1 over x over that same constant, which I would then write as 1 over x times the reciprocal of natural log of 3, which is 1 over natural log of 3. And we typically combine that in one fraction, right, as 1 over x natural log of 3. So here's the name of the game. When you differentiate a logarithm with a different base, the derivative works out the same as it usually would, except there is an extra factor where you're dividing by the natural log of that different base. So you could totally do this work if using the change of base formula. Like if I said, what's the derivative of log base 7 of x? You could, if you wanted to, say, oh, I'm going to write that as natural log of x over natural log of 7, and then the derivative of the natural log of x is 1 over x, and I've also got a natural log of 7 in the denominator. But you can also say, well, hey, I know the derivative of a log of x, regardless of the base, is going to give me a 1 over x. And then I also know that if my base is not e, or even if my base is e, I'm going to also divide by the natural log of that base. It's just that if the base is e, then you're getting 1 over x times the natural log of that base. But the natural log of e is just 1. So you just get 1 over x. So when your base is something other than e, you're going to have an extra factor of dividing by the natural log of that base. And it's also true for the chain rule versions of these questions. Like if someone said, did you make transformer noises when you were a kid? I feel like my board it's like kind of sounds like a transformer noise. Kind of. I mean, it's not like the best, but that's what it kind of sounds like. Transformer. Okay, anyway. If I want to take the derivative of the log base 2 of like x cubed plus cotangent of x, I'm going to ignore that 2 for a moment. I'm going to say, okay, I know the derivative of the natural log of some stuff, or really just log of some stuff, is 1 over the stuff times the derivative of the stuff. And I'm going to do that part first. So, okay, I'm going to get 1 over the stuff times the derivative of that stuff, which is 3x squared minus cosecant squared x. But then I also know that I need to divide by what? Natural log of 2. I would probably leave it like this and someone would hate me for it. You should probably rewrite this as 3x squared minus cosecant squared x over this x cubed plus cotangent of x times natural log of 2. So it basically works the same way the natural log does, except that you also have to throw in a division by a natural log of your other base. All right, I think the derivative of, take your pick, log base 3 of, well, I'll make it a little more exciting. Let's do log base 3 of, let me think of a good example. Sure, 2 to the x times sine of x. I've done sine so many times. Let's make it more fun, James. Come on. Let's do cosecant of x over x to the 5th plus 9. And we definitely break this one apart first. So I would totally write this as the derivative of, I'm going to do it kind of fast. Log base 3 of 2 to the x plus log base 3 of cosecant of x minus log base 3 of x to the 5th plus 9. And I would even bring down this x real fast. All right.
I need parentheses around that though, right?
Around what?
Around the first plus, log stuff. Log base 3, x log base 3 of 2 plus log base cosecant of x. You need parentheses around those, and then the minus.
No,
right?
I mean, you could have parentheses around it, but you don't. When it's addition, you don't really need parentheses. Like it could be all of this minus that, but it's really not necessary to have parentheses there. The reason I needed parentheses in that other example when it was minus is because I had to make sure I distributed the minus sign.
Okay.
But yeah, I mean, it's
because
not
one term on the bottom. Is that why?
So go ahead, say again.
Is it because it's one term on the bottom
Exactly.
and you're subtracting by the whole thing? Okay.
Exactly, yeah. If I had a product on the bottom, I would have to do minus log of a thing minus log of another thing, which is really coming from having the parentheses and distributing.
Okay, thank you.
So here, we actually get kind of an interesting result. What's the derivative of x times a constant? It's the constant. That's it. You could rewrite this if you want as the natural log of 2 over the natural log of 3. But you still just get that constant. Here, we're going to be a little bit more circumspect. The derivative of log base 3 of cosecant, well, the derivative log of a thing is 1 over the thing times the derivative of the thing. But then we also have to divide by a factor of natural log of 3. And then here, the derivative of log of a thing is 1 over the thing times the derivative of the thing. And then we also have to still divide by the natural log of our base. This one, you might have rewritten it using the, words. Using the change of base formula first. Either way is fine. But what I do want to say here is that, right, you can kind of, if you wanted to, you could factor out the 1 over natural log of 3. I don't really think that's super necessary, but you could write it as 1 over natural log of 3 times natural log of 2 minus cotangent of x minus 5x to the 4th over x to the 5th plus 9. There's lots of simplifying you can do that I don't think is super particularly necessary, but that doesn't mean I shouldn't talk about it. Okay, so let us move along to kind of the other side of having a different base. Instead of taking the derivative of like log base 3 or something, I would really like to take the derivative of something like 2 to the x. And so here's what we're going to see. When you have a log with a different base, you end up dividing by the natural log of that base, just like we did in the last couple of examples. When you have an exponential function with a different base, what we're going to end up happening is we're going to multiply by the logarithm of that, the natural log of that base. So we'll come back to this. Well, not come back. We're going to do it. So let's rewrite this. We're going to do the same sort of thing with implicit differentiation. We're going to say, okay, well, I want to find the derivative of y equals 2 to the x. I'm going to rewrite this using logarithms. So I'm going to say, oh, the natural log of y equals the natural log of 2 to the x. Bring the x down. By the way, I should point out, this is the process for logarithmic differentiation. When you have something that you want to differentiate and you don't exactly know how because there's a variable in your exponent, you start by taking the natural log of both sides. Then you simplify the side that is kind of complicated. And then you differentiate both sides. And on the left-hand side, I have to use, holy crap, the word, I'm going to use a chain rule on the left-hand side, also known as implicit differentiation, right? But it's really just a chain rule. What's the derivative of the natural log of some function of x, or the natural log of some stuff? Oh, it's 1 over the stuff times the derivative of the stuff. This happens a lot. So you should definitely be comfortable with saying, oh yeah, the derivative of the natural log of y is 1 over y times y prime. That is going to happen many, many times. On the right-hand side, it's easier than it looks. I don't have to use the product rule. The derivative of x times a constant. What's the derivative? Whoops. What's the derivative of 6x? Everybody.
6.
Sure. Everybody. And once one person says, it's like, well, someone said it already, so there it is. It's 6 for sure. Okay. So the derivative of a constant times x is just a constant. The derivative of a constant times x is just the constant. I really, really want to make sure everyone is comfortable with this, right? We don't have to use the product rule here. We could, right? You can say the derivative of x times natural log of 2 is, okay, product rule, 1 times natural log of 2 plus x times the derivative of the natural log of 2 is 0 because it's a constant. If you really want to try and differentiate using the rules of logarithms, you can say, well, it's 1 over my stuff times the derivative of my stuff. But the derivative of my stuff is 0 because the derivative of 2 is 0 because the derivative of a constant is 0. This part's all 0. So I get natural log of 2. But again, let me emphasize, just because I've seen students struggle with it so many times in the past. Natural log of 2 is a constant. Its derivative is 0. So x times natural log of 2, the derivative is 1 times natural log of 2. Right, if there
Is
aren't-
it kind of like the power rule, but you just add the ln?
I'm not sure. I wouldn't. Well, yeah. I mean, so yeah. So it's exactly like right. It's exactly like if you had x times 6, right? The derivative is x. Now I have x times this number. The derivative is 1 times that number. Yeah. There was something else I really wanted to see here. But I just want to point out, right? If someone ever asked you, like, you know, what's the derivative of the natural log of 5? They're trying to trick you. They want you to say it's 1/5. That is wrong. It is 0 because it's a constant because there's no x's in natural log of 5. Okay. So then finishing this problem off, so whenever we're trying to find a derivative using this logarithmic differentiation method, once we get to this stage here where you have 1 over y times y prime, we're going to multiply both sides by y to isolate the y prime. So I'm going to multiply this side by y and this side by y. So I'm going to get y prime equal to, I should have written the y here. Sorry, I want to write it so it's in the way I actually want it. So we get y prime equals y times natural log of 2, but we know what y is equal to. That's y right there. So we get y prime equal to 2 to the x times natural log of 2. And when your base is just some constant that is not e, or even if it is e, this is the general rule that applies. So let me write it on the other side here. In fact, I'm going to write all of these exponential and logarithmic rules real quick like here. So the derivative, I've got one good red pen and one like less good red pen, and I keep trying to pick the wrong one. So the derivative of e to the x is e to the x. The derivative of a different base to the x, like b to the x, is b to the x times the natural log of b. And actually, it's true if your base is e as well, right? The derivative of e to the x is e to the x times the natural log of e. It's just the natural log of e is 1, so we don't write that part. And then we have the logarithmic ones. The derivative of the natural log of x is 1 over x. The derivative of the log base b of x is 1 over x natural log of b. So like I was saying before, if you have an exponential function with a different base, you end up multiplying by the natural log of that base. If you have a logarithmic function with a different base, you end up dividing by the natural log of that base. And then there's also the chain rule versions. There's the derivative of e to the stuff is e to the stuff times the derivative of stuff. The derivative of b to the stuff is b to the stuff times the derivative of stuff times the natural log of b. So this is looking a little messy. The only difference between e to the stuff and b to the stuff is that, well, the bases are different. And for the b to the stuff one, you also have to multiply by a natural log of your base. Same idea here. The derivative of the natural log of some stuff is 1 over the stuff times the derivative of the stuff. Whereas the derivative of the log base b of the stuff is, I'm going to write it this way. It's 1 over the stuff times the derivative of the stuff. And then we also have to divide by the natural log of our base. I'm going to put a natural log of the base in the denominator as well. That's all the rules for differentiating exponential. Well, not quite all the rules. It's most of all the rules for differentiating exponential things or logarithmic things. So you can, if you, oh yeah, there's another way. People do this a different way as well. I will show you. So I will show you something else just to make sure that no one's doing it this other way, but yeah. But for example, we can take derivatives of all sorts of things now. So like I could ask, what's the derivative of 5 to the x? And as long as your base is a constant, you don't have to do this whole thing of doing y equals 5 to the x, natural log of y equals natural log of 5 to the x, and do that. You can just remember, oh, if my base is a constant, I just need to throw in an extra natural log of that constant at the end. So the derivative here is going to be, and the way I kind of really think about it is I compare it to e to the x in my brain. So I'm like, oh, I've got 5 to the x. Well, that's a lot like e to the x. I know the derivative of e to the x is e to the x. So I know the derivative of 5 to the x is 5 to the x, but I have to throw in an extra natural log of 5. I feel like, you know what? Some people do this differently. I will show you how people do this differently, even though I think it's kind of weird. I don't think it's dumb. I just had never learned it this way until like I was teaching, I think 17A or 17B last quarter and or 2 quarters ago. So I was like, oh yeah, my teacher did this other way. I'm like, oh, that works, but it's funky. So you can, if you really want to, do the following. You can write 5 to the x as e to the natural log of 5 to the x. Same thing. And then this x can come down right there. So this is the derivative of e to the x times a constant. All right. We know how to take the derivative of e to the stuff. The derivative of e to the stuff is e to the stuff times the derivative of that stuff. But the derivative of x times a constant, we've already talked about this at length just a few minutes ago. The derivative of x times a constant is 1 times the constant. So my answer is e to the x times natural log of 5 times natural log of 5. But e to the x times natural log of 5, which is what this is here, is really equal to e to the natural log of 5 to the x, which is really equal to 5 to the x. So this is really equal to 5 to the x times natural log of 5. I'm hoping none of your teachers did it this way, not because it's wrong, just because I don't feel like it's, I don't know. I guess I'm biased. This is a perfectly fine way of doing it. If you're just doing it this way and you want to do it this way, that's great. I think it's easier personally to remember that if your base isn't e, you multiply by the natural log of your base. So the derivative of 5 to the x is 5 to the x times natural log of 5. Or the derivative of 8 to the x squared plus tangent of x. All right, I know the derivative of e to the stuff is e to the stuff times the derivative of the stuff. So I know that the derivative of 8 to the stuff is 8 to the stuff times the derivative of the stuff. So the derivative of the stuff is 2x plus the derivative of tangent is secant squared x times, okay, everybody, what else do I have to multiply by since my base was 8 instead of e? Natural log of 8. So yeah, I don't think any of the teachers are doing that. I think it's more of a 17 thing than a 21 thing, but it's fine if they are. I don't think that.
What's the relationship between logs and ln?
They're the same. So the only difference is the base. So when I write natural log of 5 or natural log of x, natural log of anything, I'm just abbreviating a thing. So, right, when I say, y is the natural log of x, what I'm really writing, I'm just too lazy to write it, as is every mathematician ever, log base e of x. Those are the same. It's just that we encounter this particular base so often. I actually think, and I'm not 100% sure on this, but I'm fairly sure it comes from typesetting, like back when they were like trying to use less ink and use less letters in the typesetting of books. Someone was like, I don't want to frickin' write LO or typeset LOG subscript E of X every time I have to use this logarithmic function, which is the most popular logarithmic function. So instead, I'm going to give it an easier name. I'm going to use less letters, less ink. I'm not going to have to do the stupid subscript thing when I'm trying to typeset this dumb book, when they literally like put all the things into a thing to put, right? Like back when typesetting was a lot more complicated. I'm going to make my life easier. I'm going to call it something else. That might not actually be true, but it sounds true enough that it's plausible. So that's the whole thing, right? It's not actually any different. It's just an abbreviation. Just like log base 10, we often abbreviate as just LOG because we don't want to write the base 10 because base 10 is such a common base.
So we can use ln for any base?
No.
Just e's?
Just e. ln is only for base e. If you have any other base, you have to write it.
But isn't like 5 to the x power, isn't that a different base? Because 5 isn't
base e. But so the thing is, we have a rule that says for when you take the derivative of any other base to the x, it is that base to the x power times the natural log of that base.
Okay.
Because I do think it's really important that you guys are clear on this. So here's the reason why it works. So I want to take the derivative of b to the x. And so I'm going to rewrite this in a way so that I can actually differentiate it. So what I'm going to do is I'm going to take the log of both sides. I could do log base b, but I'm going to do natural log because I know how to differentiate natural log the easiest. So I'm going to say, okay, the natural log of y equals the natural log of b to the x. Whatever my base is, right? It could be 5, it could be 7, it could be 2, it could be, 1,000. It could be any positive number that isn't 1. Okay, but now I'm going to use my rules of logarithm and say, oh, that x can come down. So I've got the natural log of y equals x times the natural log of b. And then I'm going to differentiate both sides. What's the derivative of the natural log of y? Well, what's the derivative of the natural log of some stuff? What do I have to multiply by? Right? The derivative of the natural log of some stuff is 1 over the stuff times the derivative of the stuff. Equal to, okay, x times a constant. The derivative of x times a constant is 1 times the constant. Now we're going to multiply both sides by y. So that y prime is equal to y times natural log of b. But then y is equal to b to the x. So I get y prime is equal to b to the x times the natural log of b. But y prime is the derivative of b to the x. So this is the derivative of b to the x is b to the x times the natural log of b. And I will point out, it's true no matter what your base is, including e. The derivative of e to the x is e to the x times the natural log of e. But what's the natural log of e, everybody?
1.
1, right? Because natural log of e is really log base e of e, which is saying e to what power equals e? Oh, e to the first power equals e. So the derivative of e to the x is e to the x. The derivative of any other base to the x is that base to the x times the natural log of that base. Where yes, this is the log base e, where e is approximately 2.7 of whatever base you have chosen. And yeah, that base might be 5. The derivative of 5 to the x is 5 to the x times the log base e of 5. So hopefully that clears things up a bit.
Yeah, thank you.
You're very welcome. Yeah, and let me just, I'm gonna, in the chat, here's a link to the notes I'm kind of looking at in case you guys want more clarification. And these notes definitely do a couple examples where they do it this other kind of strange way, in my opinion, that I've erased now at this point, of, writing it as e to the natural log of your function and then doing it that way. That's fine. I just am not in love with it. So if I was trying to take the derivative of some non-e base to some power, it's that base to the power times the derivative of that power times the natural log of your not e base. All right. So then this leads us into the realm of, well, what if your base isn't a constant? Which means it's really not a base anymore. What if you're taking the derivative of a function to a function? And kind of the usual classic first example is x to the x, which I have to, I would imagine most of your teachers have done this if they've done already, but let's start there anyway. Even, maybe I don't know. Let's do the derivative of, I feel like x to the x is kind of, let's make it a little more interesting. Let's do x to the x squared plus 1. I want to find the derivative of x to the x squared plus 1. And I'm going to do it the way that makes sense to me. So I will point out, you could do this a different way. I'm going to show you the beginning of that, but I'm not going to do it that way because I don't think it's the best way. You could, if you wanted to, say, oh, I'm going to write this as e to the natural log of x to the x squared plus 1. Right? E to the natural log of a thing is just the thing. So this is definitely equal to that. I should still write the derivative symbol. And then you can bring down that power and say it's going to be the derivative of e to the x squared plus 1 times natural log of x. You could totally do it this way. If you did, your derivative would be, so the derivative of e to the stuff is e to the stuff times the derivative of that stuff, which would require the product rule. And then really, once you get your answer, you should rewrite the e to the stuff as this original expression. But that's not the way I want to do it, because I don't think it's the best way. I think this process of logarithmic differentiation really has something to offer. So here's what we're going to do instead. Although I'll probably finish it that way as well, just to show you. I'm going to write it as y equal to x to the x squared plus 1. Now, that is one thing you do have to do. If you're trying to use this process of logarithmic differentiation to take the derivative of something where you have a function to a function, you do have to write it as y, or usually you pick y, but you can pick f of x equal to the thing you're trying to differentiate. Because then we're going to do the process of logarithmic differentiation, which means taking the natural log of both sides. You could use any log, we're going to use natural log because it's the one with the nicest derivative. So the natural log of y is equal to the natural log of x to the x squared plus 1. And then that power comes down. So the natural log of y is equal to x squared plus 1 times the natural log of x. I should point out, although I think I've erased it. No, I haven't. So this is exactly the same as this process here. We took the natural log of both sides, we brought down the power. The difference in this next step is, for this one, we took the derivative here. The derivative of the right-hand side was just, well, the derivative of x times the constant was just 1 times the constant. Whereas in this case, we're taking the derivative of x squared plus 1 times the natural log of x. Neither of those are constants, right? X squared plus 1, as a whole is not a constant. So here, instead of saying it's just like one thing times the other, the derivative of one thing times the other, we have to use the product rule. And that's almost always going to be the case if you're taking the derivative of a function to a function, is you're going to have to use the product rule once you get to the step of taking the derivative of both sides. So the derivative of the natural log of y, like every other time we've taken it, is 1 over your stuff times the derivative of your stuff. Okay, right-hand side, I'm going to use the product rule. The derivative of x squared plus 1 is 2x times natural log of x plus, leave x squared plus 1 alone, times the natural log of, the derivative of the natural log of x, which is 1 over x. right? So derivative of that times that plus that times the derivative of that. And then you can do this next part as one step, but I'm going to show it as two. You multiply both sides by y, so you get y prime equal to y times all that. You can simplify this a little bit, but not a lot. I'm going to write this as x squared plus 1 over x. I suppose if you wanted to, you could divide and say x squared over x is x, and 1 over x is 1 over x. And then finally, and this last part is necessary, you have to replace y with what it's equal to in terms of x. Because if your function started off as a function of x, your derivative should be able to be written in terms of just x with no y's in it. So my final derivative here is x to the x squared plus 1 times all that. 2x natural log of x plus x squared plus 1 over x. Let me ask you guys, would you like to see me do it this way? I'm happy to do it this way, but only if you want me to.
I would not want to see that.
You would not?
No.
Okay.
I'm okay with the side on the left.
If anyone would, though, that's really fine. Like, I'm really happy to do it. It's going to turn out the same. I'm trying not to do it, but I'm almost not. So, right, the derivative here of e to the stuff would be e to the stuff times the derivative of this stuff. Well, the derivative of x squared plus 1 times natural log of x is the 2x times natural log of x plus x squared plus 1 times over x, right? This is the derivative of that exponent. So our final answer is e to the stuff times this, but e to the stuff is just the x times x to the x squared plus 1. So it really is the same answer either way. Let's do another one. Let me think for 1 second here. I want to do that. Yeah, okay. So the process is always these same steps. I want to find the derivative of, say, yeah, I'm going to do this one because there's a reason I want to do this one. X to the sine of x. So step 1, write it as y equals x to the sine of x. Step 2, you're trying to get that variable out of the exponent, right? The variable in the exponent is what's making it so you can't just differentiate this off the bat. So I'm going to take the variable out of the exponent and get, by taking the natural log of both sides. So natural log of y equals natural log of x to the sine of x. And you could probably even skip that step and jump straight to saying natural log of y is equal to sine of x times the natural log of x. And then finally, we differentiate both sides. Derivative of natural log of y is always going to be 1 over y times y prime. And on the right-hand side, we're almost always going to have to use the product rule, or sometimes even the quotient rule. So sine of x times natural log of x is going to be derivative sine is cosine of x times natural log of x plus sine of x times the derivative of the natural log of x, which is 1 over x. Finally, so I think you can do this next step all in one, but I'm going to show you the middle step in a second. We get y prime equal to y, which is x to the sine of x, times this stuff here, which I'm going to simplify just a tiny bit, as cosine of x times natural log of x plus sine of x over x. The intermediate step that I didn't write is the multiplying by y step, where we say, oh yeah, y prime is equal to y times cosine of x natural log of x plus sine x over x. That's it. That's the process every time. You write y equals the thing you want to differentiate. You get the natural log of both sides. You bring down your power. You differentiate both sides. You multiply both sides by y. You replace y with what it's equal to. Questions about this?
Can you repeat like the word steps again, like the process?
Definitely, for sure. Step 1, you write y equals the function you want to differentiate. Step 2, you take the natural log of both sides because we're trying to get this variable out of the exponent. We don't want that in the exponent. Step 3, bring that exponent down in front of your natural log of whatever. Step 4, differentiate both sides. The derivative of the natural log of y is always going to be 1 over y prime. The right-hand side will almost always require the product rule. Step 5, multiply both sides by this y, so that you get y prime isolated equal to y times the thing you just differentiated using the product rule. And final step, replace y with the function that it's actually equal to in terms of x, so that your final answer is a derivative that is all in terms of the variable x and you don't have any y's in it. And that's the process like every single time for when you have a thing with x to a power that's with x. And let's do one more example. Oh, and then, yeah, we should talk. Okay, yeah, we still inverse trig. Oh, okay. Yeah, one more example, and then we'll talk inverse trig for a hot second. I might not get to that weird formula that I asked you all about at the beginning, partially because I don't love it, partially because it's just not the most important thing. But we can definitely talk about it next week. Or if you have questions between now and next week, put them on this. Like especially if you have questions about the weird derivative of f inverse stuff, write a discussion post in Canvas, and I will definitely answer it there and give you guys some guidance that all of you can see. So if you have weird questions about how do I find the derivative of f inverse evaluated at this weird point, or the slope of f inverse at some weird point, I can definitely talk about that later. But it's not super pressing, I feel like, right now. So instead, I want to find the derivative of, I'm going to change this one up. Let's find the derivative of tangent of x to the x cubed power. That looks gross. All right, same 6 steps. First step, y equals the function I'm trying to differentiate. Second step, take the natural log of both sides. And I feel like you could probably gloss over this step and jump straight to the third step where the power comes down in front of the logarithm. So the natural log of y is equal to x cubed times the natural log of tangent of x. Or you could probably jump straight from here to here. And then differentiate both sides. Derivative of the natural log of y is 1 over y prime. Derivative of this product is, derivative of the first thing is 3x squared times the second thing left alone, natural log of tangent of x. Oh, there was something I'm going to go back to the previous problem just a second, just because I want to answer a question that no one asked, but it is important. Plus x cubed times the derivative of the natural log of tangent, well, it's 1 over the stuff times the derivative of the stuff. Secant squared over tangent doesn't simplify in any meaningful way, so we're just going to leave it as is. But then we're going to multiply both sides by y. So we're going to go, y prime is equal to y times all of that stuff, which is 3x squared natural log of tangent of x. And I would probably simplify this as x cubed times secant squared of x over tangent of x. And then finally, I would write my final answer by replacing what y is equal to. Oh, y is equal to this stuff right here. So that's going to go in for y. And we get y prime equal to tangent of x to the x cubed power. By the way, whenever you're differentiating something that's kind of like you have a power that's a variable, the original expression always shows up, right? In each of these problems, the derivative of the thing has always been part of the answer. And even for the ones where the base is a constant, right? When you're taking the derivative of 2 to the x, you get 2 to the x times natural log of 2. Or the derivative of e to the stuff is e to the stuff times the derivative of stuff. So whenever you're differentiating something that's exponential in nature, or where you have a variable in the power, it's a guarantee that that original function is going to show up as part of your answer. So the answer here is y, which is tangent of x to the x cubed power times all this trash. 3x squared natural log of tangent of x plus x cubed secant squared of x over tangent of x. Whew. Good times. Let's see. Okay, yeah. Yeah, sure. There was a question. So on the previous example, there is something I wanted to point out that I'm glad no one asked, but it's still a question I'm going to ask, even though the answer is no. So the question that no one asked, that I'm glad you didn't ask, is, isn't sine x over x equal to 1? And the answer is no. But I want to point out, oftentimes students in the past have been like, hey, James, isn't that 1 right there? Can't you simplify that? And the answer is definitely not, because what they were actually thinking of was the limit as x goes to 0 of sine x over x. That would for sure be 1. But sine x over x on its own without a limit is just sine x over x. So I just wanted to point out, in case anyone was curious, not that you have to admit it, this is not 1. Its limit as x goes to 0 is 1, but this on its own is just sine x over x. But I imagine none of you were thinking that, because you all are like, yeah, I know that sine x over x is a function. It has all kinds of stuff.
Yeah, I had to take a second to think about it.
Sure.
And I was like, oh, kind of x over x, huh? And I was like, oh, it's a limit. No.
Exactly. Good.
Yeah.
But it's easy to want to make that and be like, oh yeah, I feel like I could make that much nicer. We cannot. All right, so all of this, well, not all of this, but a lot of this is leading us to then be able to take derivatives of some very specific inverse functions. And yeah, we've got enough time to at least do inverse sine. So I want to find the derivative of the inverse sine function, which I suppose I should talk about first. Right, so inverse, oh, excuse me, goodness. Where'd you go, inverse sine? Did I lose you? Yeah, fine. So inverse sine is kind of funky, right? If I graph the sine function, so y equals sine of x, has the usual look. And the problem with trig functions in general and their inverses is that trig functions, unlike a lot of other functions that we find inverse functions of, are not one-to-one. If I draw this trig function here, sine of x, which looks vaguely like this, it goes on and on and on. This function doesn't pass the horizontal line test, which is the test for being one-to-one. And the problem with that is, well, I mean, it's still a function, but if you try to find the inverse will not be a function. Because when you find an inverse, you're switching x and y. So here's the graph of the inverse relationship, not function. If I do x equals sine of y, I essentially am just switching x and y to find the inverse. Basically, you're just, instead of drawing the graph on the x-axis, you're drawing the graph on the y-axis. So it looks like, I'm always bad at drawing on the y-axis. It kind of looks like that. And I bet you guys can all say, oh, that's not a function, because it fails the vertical line test. So if a function fails the horizontal line test for being one-to-one, its inverse relationship is going to fail the vertical line test and not actually be a function. So what do we do with that? Well, we say, this function is important. Most functions are like, I don't really care. Okay, its inverse isn't a function, well, great, no big deal. But sine and cosine and tangent and all the other trig functions, which none of which are one-to-one, all of which fail the horizontal line test, we really care about these functions. We would like there to be inverse functions. So what do? We take the sine function and we limit the domain. So I'm going to pick a domain where it is one-to-one. And we're going to pick the domain from negative pi over 2 to pi over 2. Because in that domain, it is a function, or in that domain, it is one-to-one. It does pass the horizontal line test. Any horizontal line I draw only goes through one of the points in this section here. Yeah, it goes through other points out there, but we're excluding those. So what we're going to do is we're going to do the same thing here. We're going to say, okay, well, if x goes from negative pi over 2 to pi over 2, if we switch x and y, that means y is going to go from negative pi over 2 to pi over 2. We're going to get this little section right here. So the actual inverse function, not the inverse relationship, but the inverse function, which I'm going to try and draw a little bit more nicely here. Goes from the point negative pi over 2, comma, negative 1, right? Because again, right, this is the point. Oh, sorry, I switched it accidentally. This here is the point negative pi over 2, negative 1. And this here is the point pi over 2, comma, 1. And so if you're switching x and y, you're literally switching x and y. This is the point negative 1, negative pi over 2. That's negative 1 there, that's 1. And this is the point 1, comma, pi over 2. And this is my inverse sine function. it's kind of a not very exciting function in that there's not a lot of it, right? You only got, so this is a function. Its domain is -1 to 1. Its range is -pi/2 to pi/2. And that's it. There is no more to it. You get nothing else. I'm thinking of Willy Wonka. You lose. You get nothing. Anyway, from the original Willy Wonka. I mean, right? Gene Wilder, the best. Anyway, tangent. Well, sign, not tangent. The point here that I'm trying to make is that you have to do this for every one of the 6 trig functions if you want to talk about its inverses. You have to restrict the domain of the original function so that when you flip or interchange x and y, the inverse function actually is a function and not something that fails the vertical line test. So now I would really like to take the derivative of this, right? And there should be a derivative because this definitely looks like, right, there's some tangent lines that have some slopes. So how do we take the derivative? Well, it definitely comes down to the fact that we're going to use this. So if I want to say y equals the inverse sine of x, it's equivalent to saying that x is equal to sine of y. Kind of like, not exactly like, but very similar to when you might have first learned about how the logarithmic functions work. Someone might have said, okay, well, I'm trying to find the inverse function of like 2 to the x. And so I'm going to interchange x and y, x equals 2 to the y. And I'm going to try and solve for y. And really what we do is we're like, well, we don't have a good way of doing this, so we're going to make up a new function. We're going to make up a new function that is the inverse function of 2 to the y. It's going to be log base 2 of x. And the logarithmic function is literally the function that undoes what 2 to the x does, right? 2 to the third is 8. Log base 2 of 8 says 2 to what power equals 8? Oh, with the third. So here you input 3 and you get out 8. Here you input 8 and you get out 3. Same idea here, right? You're saying, oh, I want the function that undoes what the sine function does. So sine of pi over 3 is root 3 over 2. Inverse sine of root 3 over 2 is equal to pi over 3. So sine of pi over 3 equals root 3 over 2, right? They're the same, they're just opposites. The difference here is that in this case, y is limited. Y has to be between negative pi over 2 and pi over 2. We have a limited range, which isn't true for a lot of other inverse functions. Okay, I know we're almost out of time, so I'm going to cut to the chase here. I'm going to differentiate both sides. What's the derivative of x? It's 1. What's the derivative of sine of some stuff? Oh, it's cosine of my stuff times the derivative of my stuff. Okay, let's solve for the derivative. This is where things are going to get a little more complicated. So I'm going to solve for the derivative. I'm going to get y prime equals 1 over cosine of y. Now the problem here, just like in the previous ones, is I have a y in my answer and I don't want a y in my answer, right? It should be just in terms of x, because my original expression was y as a function of x. So here is what you don't do. We're not, I mean, you could do this, but it's lame. We're not going to say that the answer is cosine of y, which is sine of x. Sorry. Cosine of, I'm definitely not going to write that it's cosine of inverse sine of x. Some people do it this way and then work from there. I find that to be not very satisfying. So this is fine, but not really. It's not the answer we're looking for. Instead, we're going to use triangles. And this is important. I think even if some people use trig identities, which is also fine, but triangles are better because you're going to use triangles in Calc 21B when you're talking about trig substitution. So this is a good thing to do now because we're going to do it later. So I'm out of room. Where do I want to write things? Just look over here. Sorry. I'm going to use this. Sine of y, I'm going to think of y as an angle because I take sine or trig functions of angles is equal to x. So sine of y equals x over 1. I can draw a triangle where that's true. It's a right triangle. The angle is y, and sine is opposite over hypotenuse, so sine of y is x over 1. That's why I wrote it as a fraction, so that I can think of it as, oh yeah, opposite over hypotenuse. Pythagorean theorem to find this side here. Let's call it a. A squared plus x squared equals 1 squared. A squared equals 1 squared is 1 minus x squared. A equals the square root of 1 minus x squared, which we can't simplify any further. But now check it out. Y prime is equal to cosine of y. Cosine of y is a over 1, or square root of 1 minus x squared over 1. So this ends up being 1 over cosine of y, which is the square root of 1 minus x squared. That's it. That's the derivative of inverse sine. One thing I want to mention, because this is something we have to think about, but it actually always ends up working out all right. Technically, I should have said that this side was really plus or minus the square root of 1 minus x squared. So when I took cosine of y, I could have actually gotten a negative thing. But the truth is I really couldn't. And I erased the reason why. Why? Haha. I erased the reason why. Y has to be, and so I erased the graph, I know. But before I said, what does y have to be between? Negative pi over 2 and pi over 2. Well, if you think about the unit circle, negative pi over 2 and pi over 2 is which two quadrants of the unit circle? That's a good question, James. Let's see, pi over 2 is up here. Here's 0. Here's pi. Here's 3 pi over 2, but I actually want to go backwards and go that way to negative pi over 2. So here I am on the right side of the unit circle. Quadrants 1 and 4, where cosine is always positive. Cosine is positive up here, cosine is positive down here. So I can definitely say, even though I thought for a second it might be plus or minus, oh no, it's definitely always positive. Because we're in the right place. And the thing that's nice is that all of the rest of these inverse trig functions work out the same sort of way, where you could have a plus or minus, but then it works out to always be the sign that we want it to be because you're in the right quadrants for it to be the sign you want it to be. So we're out of time, but I will say the rest of the inverse trig derivatives work very much the same way. You start by saying, okay, y equals inverse trig function of x. You rewrite it as x equals regular trig function of y. You differentiate both sides. You get 1 on the left. You get derivative of trig function evaluated at y times y prime. And then you figure out what cosine of y is, or secant squared of y, or whatever your trig function of y is, by drawing a triangle and finding the unknown side using the Pythagorean theorem. We'll definitely talk more about this on Monday, but I wanted to make sure I got one in before then. All right.
So when using the triangles, you would use sine of y instead of the cosine.
Well, yeah. So like if I was doing, so I'll just say real briefly here. If I was doing a different one, so for example, if I was trying to find like the derivative of inverse tangent, and you're welcome to go if you need to go, but I just want to, I'll say this real quick. If you're trying to do this, I would start by saying, okay, y equals inverse tangent of x. And then I would rewrite this as tangent of y equals x. I would differentiate that. Derivative tangent of some stuff is secant squared of the stuff times the derivative of the stuff equals 1, right? Derivative of x is 1. I would solve for y prime. Y prime is 1 over secant squared of y. And then to figure out what secant squared of y was, I would go back to this. Tangent of y equals x. Or if you prefer, tangent of y equals x over 1. But now it's tangent, not sine. So I'm going to draw my triangle saying, okay, well, tangent of y. Tangent is opposite over adjacent. So tangent of y is x over 1. So opposite over adjacent is x over 1. And then I find the third side using the Pythagorean theorem, which is the square root of x squared plus 1. And then I'd say, oh, secant of y. Well, cosine of y is adjacent over hypotenuse, so secant is hypotenuse over adjacent. So secant of y is the square root of x squared plus 1. So this is going to be 1 over the square root of x squared plus 1 squared, which is just 1 over x squared plus 1. So it's the same type of process every time. Every time you are saying y equals inverse trig function, then you're rewriting it as regular trig function of y equals x. You're differentiating the left side. You're getting the derivative of y times y prime equals 1. You're solving for y prime, and then you're figuring out what this is by using the triangle you get from this.